Multi-agent decision-making problems, often formulated as optimization tasks, arise in a wide range of application areas, such as in collaborative robotics, intelligent transport systems, and integrated energy systems, to name a few, where a collection of agents work together to achieve a common goal. A common framework for multi-agent decision-making is the decomposition coordination approach, where the agents solve their own local subproblems and a central coordinator accounts for the coupling or the interactions between the different agents, thus facilitating a coordinated action. In the traditional optimization framework, each local agent requires analytical expressions that relate the local decision variables to the local objectives and constraints in every subsystem. However, obtaining reliable models is a time-consuming and tedious work, which is often one of the biggest bottlenecks in many application areas. A class of optimization methods, known as Bayesian optimization, is a promising alternative that circumvents the need for detailed mathematical models. Here, the system is considered to be an unknown black box that can be queried through a series of experiments. The data observed from such evaluations can then be used to find the optimum. However, in the context of multi-agent systems, the observations resulting from querying a subsystem often cannot be shared with the other subsystems due to data privacy concerns. Also, the local acquisition function in each subsystem typically does not account for the coupling to the other subsystems. Despite the growing popularity of Bayesian optimization, decomposition coordination frameworks for Bayesian optimization has received very little attention in the literature. To address this gap, this paper proposes a multi-agent Bayesian optimization framework that is capable of solving black box optimization problems defined over a multi-agent network coupled via shared variables or constraints. In the proposed approach, we separately apply Bayesian optimization to each subproblem where we learn a Gaussian process surrogate model for each local cost function based only on its local observations. To enable the required coordination, we propose to incorporate additional penalty terms to the local acquisition function. We then derive an expression for the penalty terms using the alternating directions method of multipliers framework. Note that the choice of the local acquisition function is independent from the coordinating term. Hence, any acquisition function proposed in the standard Bayesian optimization framework can be directly used in our multi-agent Bayesian optimization framework. Moreover, the choice of the acquisition function can also be different between the different subsystems. We demonstrate the performance of our proposed multi-agent Bayesian optimization on the problem of fuel-efficient vehicle platooning, where a collection of vehicles must coordinate to decide on the speed of the platoon that optimizes the overall fuel efficiency. We show that our proposed multi-agent Bayesian optimization framework is capable of quickly identifying the optimal platoon speed, even with no prior knowledge of the relationship between speed and fuel consumption in any of the vehicles in the platoon. To this end, this work represents a first step towards a decomposable Bayesian optimization framework for multi-agent systems.